Welcome to The Explainer. Today, we're investigating what I can honestly only describe as an absolute engineering heist. We're going to track how developers literally tunneled right under the rigid constraints of modern computing to pull off this massive mathematical breakthrough. It's a completely fascinating ride into the true next generation of decentralized finance and AI, showing us how we're totally reimagining how machines process math. Now, I really want you to keep this massive, almost impossible question in mind as we go. How do you do complex trigonometry on a computer that literally cannot understand decimals? Right? It sounds totally absurd, but this is the exact mystery we're cracking today. We're going to figure out exactly how decentralized systems handle these incredibly complex fluid pricing curves without ever relying on traditional floating point math. Section 1, the mark, the FPU gambler. Okay, let's dive into this by taking a look at our primary target here, the legacy hardware problem known as the floating point unit. To really grasp the problem, we have to contrast two very different parts of a computer's physical brain. On one side, we have the FPU gambler. You see, to handle complex math incredibly fast, the FPU essentially just guesses. It frantically throws darts at a board using these hidden proprietary corporate seed tables burned directly into the silicon. It's super fast, sure, but it's probabilistic. Then, on the exact opposite side, you have the arithmetic logic unit, or the ALU surveyor. The surveyor is strict. It's discrete and totally deterministic. In the ALU, 1 plus 1 is exactly 2 every single time, universally verified. But because the FPU is constantly chopping off tiny decimals, something developers call the 23rd bit chop, just to squeeze numbers into memory, it creates what researchers call the wood chipper effect. Think of the FPU like a giant blender. Once your exact data goes into that digital smoothie, well, you get the permanent destruction of exact data provenance. You can literally never perfectly reverse engineer that calculation back to the exact original fruit it came from. The mathematical chain of title is just gone forever. And here is the truly staggering reality of this hardware limitation. An estimated 80 to 90% of modern AI compute cycles actually rely entirely on these hardware approximations. That's huge. When massive language models are doing their heavy lifting, they're mostly just using hardware that fundamentally guesses the nearest mathematical truth. It's a massive systemic problem of estimation over real arithmetic. Which brings us to Section 2, the vault, hitting the trig wall. You see, you can't just guess your way through high-stakes, decentralized finance. The Ethereum virtual machine, or EVM, acts as our vault here, and it strictly demands perfect bit-for-bit consensus across tens of thousands of global machines. It absolutely cannot tolerate the compounding rounding errors and non-deterministic drift of the FPU gambler. Trying to force smooth, continuous trading curves into discrete floating point approximations, it just causes massive informational debt. Legacy automated market makers, or AMMs, run into brutal obstacles here. They try to use heavy floating point trigonometry, which the EVM doesn't even natively support. This leads to non-deterministic drift, risks severe consensus breaks, and causes massive computational bloat. And ultimately, it leaves liquidity pools completely vulnerable to nasty arbitrage exploits, like dust grinding during volatile market swings. Nobody wants that. Section 3, the tunnel, square root integers. If we can't go over the wall using floating point math, we have to dig under it, right? This brings us to the brilliant mathematical heist discovered in the best ape square root integers repository. These researchers actually found a way to bypass this trig wall entirely, resurrecting division-free integer geometry. Now, what's really interesting about this slide is the sheer architectural leap it represents. Developers realized they absolutely had to ditch those heavy, gas-guzzling, double-sequence generating functions that legacy systems were trying to use. Instead, they moved to an incredibly elegant, single linear integer recurrence. We're talking about a total shift from mathematically bloated decimal approximations to lightweight, incredibly fast executions using pure whole integers. And this elegant shortcut looks exactly like this. an equals 2a n minus 1 plus n minus 1 a2 minus 2. Now I know, don't let the math scare you off. Simply put, this single sequence acts like an on-chain magic trick. It dynamically generates exact rational approximations of square roots without ever relying on decimal guesswork. By just ratioing a single integer sequence against its predecessor, the system locks in undeniable truth using only whole numbers. Section 4. The score. The square root hack. This brings us to the absolute climax of our explainer. let's look at the exact numbers that made this zero decimal precision possible. Think about the number 1.0001. In modern AMMs like Uniswap, 1.0001 is a vital base tick multiplier used to track price intervals logarithmically, which is especially critical for concentrated liquidity pools involving stablecoins. But calculating powers of 1.0001 on a system that demands pure whole numbers, that's a massive, massive hurdle. Historically, it forced developers to rely on really complex, gas-heavy, fixed-point approximations. But the square root integer hack bypasses all of that completely. By plugging into that single linear integer recurrence we talked about, developers literally tricked the computer into generating nearly perfect irrational square roots. To hit that exact 1.0001 target tick, they used the remarkably simple ratio of 10,202 over 101. They nailed the required math using absolutely nothing but pure, verified whole integers, basically kicking the FPU completely out of the equation. So, the crucial point here is the sheer accuracy of this approach. At just the second level of recurrence, that simple ratio of 10,202 over 10,001 hits a minuscule 0.00485% error rate. It achieves staggering precision, well within required tolerances, locking in absolute deterministic truth without ever asking a microchip to throw a dart at a board. To fully integrate this exact guess-free math, the framework uses 3 brilliant steps to completely bypass the FPU. Step 1. Anchor the coordinate system to a equals 1, known as side A normalization, which effectively straightens messy curves into exact lines. Step 2. Replace heavy trigonometry with discrete reciprocal shifts across a rational lattice. And Step 3. Implement global remainder tracking, or GRT. Instead of just rounding off the tiny fractions, GRT natively tracks the mathematical leftovers as a strict machine state. We have officially unblended the digital smoothie, folks. And this brilliantly illustrates the real-world payoff of our heist. Notice the massive drop in the bar chart here? When you switch from legacy floating point calculations to this pure integer geometry, you trigger a staggering 74 times reduction in metabolic energy costs. Because we're stripping out insanely costly division and square root operations, and replacing them with simple addition and multiplication, the energy required drops to an astonishing 0.05 picojoules per operation. That's just wild. Section 5, Age of the Surveyor, Bit-Perfect Results. We have officially abandoned spatial approximations for absolute integer geometric rigor. We've moved from a probabilistic guessing game that risks fatal stack overflows to strictly unbiased orientation. The entire state transition now executes in flat, instant O of 1 computational complexity. Let's move to this next thought and see how all this builds into a profound philosophical leap, perfectly captured by this quote from the architecture documentation. Ticks are what we see, quantiscale is what we might learn. We've replaced the computational illusion of floating point mathematics with pure geometric truth. It completely redefines the foundation of both decentralized finance and the future of infinite context AI inference. We've traced an incredible journey today, tunneling under decades-old technical walls to bridge the gap between messy, continuous reality and strict deterministic machine execution. So I want to leave you with one final provocative question to ponder. Now that this deterministic blueprint is in your hands, what will you orchestrate with this new bridge between math and physical reality? Thanks so much for joining me for this explainer. Keep exploring, and I'll see you next time.